Everybody's everybody's welcome to come get all the pizza that they want here. Today I'm pleased to introduce Dr. Yao Li. He is currently an associate professor at the University of Massachusetts at Amherst in the Department of Mathematics and Statistics. And he received a PhD in mathematics from the Georgia Institute of Technology and a Bachelor's of Science in Mathematics from the Shanghai Jiao Tong University. And his primary research interests are applied probability and applied dynamical systems. His research interests also extend to a variety of problems in machine learning, statistical mechanics, and neuroscience. And we are glad to hear more about his research.
Okay, thank you for the introduction. So today let me introduce something about the methods rather than the concrete mathematical problems. So that's something that one of my research direction, and it involves lots of my students, postdocs, and other younger collaborators. Okay. So let's talk about if we have some stochastic dynamics. Say maybe you have some ODE and you add some noise, and then but the dimension is really high. Then what can you do? And also, what can the simulation data help us? So let me start with something that I always want. So that's I mean, the basic idea is that we want to try to see how can we do something in really high dimension. And the idea is that in high dimension, well, you can always do simulation, you can always gather lots of data. But there are also many things that becomes much more difficult in higher dimension, particularly the traditional PD solvers. For example, you take the spatial discretization, well, that's almost out of question in the true high dimensional space. Okay. Then the question is that what can you do? So I will say a few things. So I mean, I believe they are more or less related to methodology practice in different areas. For example, we have the Fokker-Planck equation about the probability density function. We have the geometric equidistant, means that how stable, how stochastic stable your model is. We have the eigenvalue and eigenfunction is particularly important in studying the oscillators. And then we study the quasi-potential function, which is very important in things like rare events sampling or the metastability. Okay, so let me start with some Van der Poel models. It's basically some simple oscillator with very rich bifurcation behavior. I started this example because there is a lot of difference between, you take the ODE and then you take some simple convolution with Gaussian and the actual stochastic dynamics. So here, let's we start with some Van der Poel oscillator, and then we assume that so on the left part. On the left panel, it's just the deterministic one, and then you have small limit cycle there. Looks very good. And then you add just a little bit noise, such that the trajectory still visually looks smooth, but then suddenly you have this stochastic mixed mode oscillation that it's not a small limit circle anymore. Actually, you are jumping between small limit circle and the big limit circle. And if you really simulate for long enough time, you can see that the trajectories will fill this entire block. So that's called the stochastic mixed mode oscillation. So I use this example to highlight that, well, that's why we do need to study what happens under the noise, because there are lots of intrinsic noise in like a biochemical oscillation or like in neural oscillator and so on, and also in like ecology and like in the ecology model. So we really need to understand. But on the other hand, I mean, there are always some difficulty in using the rigorous methods to get the full picture. I mean, the rigorous proof you can do something with rigorous proof, but there are always some gap. So let's say that usually we say that we start from some stochastic, we start from some deterministic dynamics, maybe just an ODE, maybe just some neural oscillator. And then we add some small noise. Okay, then we get something like a Fokker-Planck equation. So the Fokker-Planck equation basically tell you that what is the probability density function and how it evolves with time. And then assuming that your deterministic dynamics is kind of well behaved, then in many situations you should expect the existence of some invariant probability measure, as long as it's not like you don't have the problem of finite time blow up. Usually you should have this, and then you should have a steady state for Planck. Okay. And then there are lots of results. There are lots of results about when do you have invariant probability measure and how fast do you have the convergence and how does the invariant measure concentrate. However, if you take a look at all of those results, including my own paper, you can see that the information you get from those theoretical results it is still not precisely what we see in numerical simulation. So that's why we need both. We need the theoretical guarantee that we have existence, we have convergence, but we also need to know what they exactly look like. For example, if I start from some chaotic attractor called Rossler, it's basically like the one butterfly wing of the Lorentz. Okay, and then you have some strange attractor, you have chaos, you have noise. Okay. And then the question is that let me add some small noise. Then what does this look like? Well, turns out that if you work on the reverse proof, then you have the existence, you have the concentration, you have many results. But this still does not tell you what does the probability density function look like. So in fact, it looks like this. It's probably, I mean, that's of course this is the projection because I cannot visualize a 3D probability density function because I mean our screen is too deep. So how to project everything on the XY plane? Okay. So you have something like this. That's from the numerical simulation. So the question is that how can we get this? And what if it's not a 3D? It's even higher dimension. Like you have maybe 10 neurons and you couple 10 neurons together, then you have dimension either 20 if you use something like Morris-Leclerc, or maybe 40 if you use Hodgkin-Hawking. Okay. So the question is that how can we compute? Let's start from the simplest one, the invariant one, because if you can do the invariant density function, then you can do the time-dependent density function. So you can always, of course, you can just do the classical spatial discretization like in your undergraduate textbook. Right? But the thing is that you cannot even do this in 3D because the curse of dimensionality. And the other way is that you can run Monte Carlo simulation. You can divide the domain into lots of small bins and just run a long trajectory, and then you count how many samples I have in each bin, and then you can have some estimated density. And probably you can also smooth it by using something like the kernel density estimator. But of course, if you really do, you will see that the KD itself has lots of drawback. So for example, if you start from some extremely simple thing that you have a limit cycle that is just the unit cycle, just the unit circle, okay, and then you add some noise and you know everything basically. And your Monte Carlo simulation usually look like this, even if you run a very long trajectory. Why? Because you divide your space into too many bins, and in one bin you can only collect that many samples. So if you collect maybe say 100 samples, then your relative error is around 10%. So which means you need a huge number of samples in order to make the result look reasonably well. Okay, so this comes our first attempt. So that's dates back to a few years ago. So it's me and my colleague and also my previous postdoc, Dr. Zhai. So the first attempt is that let's try to combine the advantage of Monte Carlo and numerical PDE together. So which means let's say that we do some undergraduate numerical PDE, we take the spatial discretization, but we do this without a boundary. and then we use Monte Carlo simulation as a reference. So which means without a boundary, then the numerical PDE this does not give you a full matrix, which means now you have more variables than equation. It's just a linear constructor. It's not a linear system that you can solve. However, on the other hand, you also have Monte Carlo. So which means you can use your Monte Carlo data to constrain. This gives you a variational problem that you want your solution to be, satisfy the numerical PDE linear relation. At the same time, you want it to be as close to your Monte Carlo data as possible. So this is called the least norm solution. And then you can see that the least norm solution has a much better quality than either you just use numerical PDE or you use Monte Carlo itself. Why? Because numerical PDE, if you really do it, you can see that there are lots of difficulties coming from, for example, the boundary conditions. Okay. So then you get the first result, then the first improvement, that you have this data-driven PDE solver, that it does not rely on boundary condition, because what is the boundary condition of Fokker-Planck? Well, the boundary condition of Fokker-Planck is that it vanishes to zero at infinity. So which means on the finite domain, it's really difficult to prescribe a boundary condition. So usually you have to do some other things. And then you have high resolution, but you still have to solve some linear system. But that's some important first step. It motivates all the basically all the works after that. Okay. So the question then, what is the mechanism? Why it makes the solution dramatically better? So the answer is that you have the Monte Carlo simulation. It has lots of randomness. So which means the error is basically random vector. And then what does the optimization problem do? Well, it actually projects this random vector from very high dimensional space to the kernel space of your linear constraint, which has much lower dimension. And this projection reduces the random error dramatically. So that's the error bound we get. So if n is the set, then the error is reduced by n to the power of -1/2. That's the theoretical upper bound. But empirical performance is a lot better in this. Why? Because there are also something that is difficult to quantify, that the projection itself. It not only pushes the it not only do the projection, but it also pushes the error term to the boundary. So which means at the center it looks a lot better. So this can be done by measure the principal angles between those two subspaces, but that's not something that can be easily calculated by hand. You can numerically calculate the principal angles. You can justify these things, but it's difficult to calculate it by hand. Okay, so then start from here. We can do lots of extension. So the first extension is still finite difference, but we can use it. We can use it to do 3D and 4D problems. I mean, as long as the computer memory allow you to do the spatial discretization, you can do it. Why? Because you can do the divide and conquer. You can divide a very large domain into lots of small blocks, and then you run one solver on one block. And because this cost of solving a linear system is definitely super linear. It's usually if you use a sparse matrix, it's quadratic. So which means the divide and conquer save you lots of computational time. And also you can see that the error term concentrates at the block boundaries. So it works very well for 3D and 4D problem. So that's how I get this steady state distribution of the Rossler oscillator. But I mean here, the main technique we developed in this paper is that we use this shifting block method. Why? Because if you do it naively, then you will see that I push all the errors to the boundary of blocks, which means on the interface it looks really ugly. And how can you do that? How can you eliminate those interface? So the idea is that you should draw the block again. You should construct another sequence of blocks such that the new center covers the old boundary, and then you run this algorithm again. Because the algorithm always pushes the error to the boundary of the block. So after a few iterations, you can see that all the interface errors are gone. Okay. So that's that's the Rossler. that's the Rosler, and that's that's the solution that I showed to you before. And you can also see the invariant density on different slices. So I cut off a few XY slices for different z, and I just want to show you what happens here. And yeah, that's the projection project to the XY plane. Okay, so that's the first extension. And the second extension is that even if you have this divide and conquer technique, you still need some spatial discretization. But if the dimension is really high, then that's still a big headache because you simply do not have the memory to store that many grids. So what can we do? Well, in the higher dimension, turns out that the artificial neural network is a better approach. So which means, yeah, we still run the Monte Carlo simulation, and we have the Monte Carlo simulation data at different points. And let's have a new optimization problem, meaning that we want to minimize the sum of Monte Carlo error and also this residual coming from the operator. So here, if it is a finite difference, then it's just it's a it is a linear algebra problem. But you can always do this by replacing this u by some artificial neural network to approximate this u. So this gives you something like it's basically like the pins, physical informed neural network, just with a lot of help from the Monte Carlo. And it turns out that it converges dramatically faster than the classical pin. If you really have trained pins, you will know that the speed of convergence is really quite slow. But here, with the help of Monte Carlo, you can see that the speed of convergence is dramatically faster. So you have two loss functions. One is that I want to make sure that the result is close to my Monte Carlo simulated data as possible. And the second one is that I want to make sure that I act the PD operator onto the neural network, and I want to make the residual to be as small as possible. Okay, so which means we have two loss functions, and then usually we design two different training sets. And here there is a small trick. There is a small trick that it applies to basically all of those methods. Is that say that those two laws they actually have very different scales. So in the beginning, you just start from some arbitrary thing, and then you will say that your L2 is very big and L1 is reasonable. But later, because L1, the Monte Carlo, it has the intrinsic noise there, so you cannot reduce it to 0. But L2 you can reduce it to 0. So later it's switched. L2 becomes dominant. So how can you train these two loss functions? The simplest trick is that you can just do this alternating item, means that you train two loss functions alternatively. Okay, so you can train two loss functions. One you move one step with L1 and another step with L2, and then we use the fact that this item optimizer is basically almost scaling free. Okay. So turns out that here we can tolerate lots of error, lots of uncorrelated noise. So this way can be just some very rough approximation of the true solution. Okay, and for example, let's take a look at a 4D example. Okay, take a look at the 4D example, still a ring example, but it's like the steady state concentrates on a 4D sphere. And then you can see that we just use a small feed-forward neural network, and then that we can basically get the solution on each slices of this 4D domain. And then the third extension is that we then I have one student who is currently at Boston University, by the way. Then we take a look at the time-dependent one, and it turns out that it's not a simple extension. Why? Because when you have this UT term, then you have less constraint on the T direction. So the neural network training is a lot different. So here alternating atom does not work that well. It still converge, but not converge as fast as before. And then we develop a new way to balance these different losses. So you have some theta, and theta is not arbitrary. So theta basically depends on the gradient from the last epoch. So in this way, you can make sure that two loss terms are contributing roughly equal. Okay, so that's the first thing that what is the steady state, and what is the solution to the Fokker-Planck. And the second thing is that so how fast do we have the convergence to this steady state? That's also important because it's not just about the stability, it's also about this sensitivity. Why? Because say if you have something stochastic different equation, for example, you have a steady state, and then you want to understand how the change of some parameter or maybe some additional terms to hold the change your steady state. Then turns out that it entirely depends on how fast you have the convergence. So the faster convergence is, then the more robust it is against the small perturbation. The less likely that you change some small parameter, then suddenly the entire steady state moves. Okay, then the question then how fast do we have the convergence? So usually we measure it by measuring this geometric ergodicity. Okay, so which means what's the exponential speed of convergence? It's basically like the special gap. Okay. And the problem is that if you really work on the classical method like finite difference, then you take the finite difference of the operator, and then you take a look at its eigenfunction and eigenvalue. That's the cost is very high. You can only do this for 2D. So the idea is that we do the coupling. So what is coupling? Coupling means that you want to run a pair of stochastic different equations and make sure that the two marginals are still equal, but in the product space, they are doing something else. And then you couple them and you put them together when they first meet, and then you never separate them. And then turns out that the speed of convergence in total variation norm is bounded by the probability that you have not coupled yet. That's called the coupling inequality. So make use of that one, then we have the lower bound and the upper bound. So the lower bound is like, okay, so the speed of convergence is at least that first. And the upper bound is like, I cannot converge faster than this. So the lower bound is given by you just measure the coupling rate. So starting from different initials, and then you want to design the best way to couple them. And the upper bound is like you want to divide the domain into two parts, and then say when do you see the first exit time? Because if you do not exit from a partition, you cannot couple at all. Okay, so then that's some numerical details about how we do this coupling technique. So usually we either use same noise or we use measuring noise. So meaning that if the noise on one trajectory go left, you want the other noise in the other trajectory to go right. Okay. And when they are close enough, then you want to switch your strategy. You want to move to the maximum coupling by just comparing their probability density function. And then you can see that yeah, that's numerically consistent with actual coupling speed. And then you can get some very quantitative bound of the speed of convergence. So which is very difficult if you do the rigorous proof. That's why I say that yeah, there are always some limitation in rigorous proof that you have to bridge the gap by using computations. For example, even if some simplest SIL, you have some degenerate noise, and then yeah, you should have invariant probability measure because you can easily say that there should be a Lyapunov function. However, what does the steady state look like, and how fast do you have the convergence? Well, it turns out that literally almost all the existing methods only tell you that the speed of convergence is it exponential, is it sub-exponential, or is it power law? But it does not tell you anything about the bound. You can only get that the speed of convergence is exponential, but you don't know what is this exponent. You only know that it's strictly bigger than zero. So it's difficult, very, very difficult to get any quantitative bound. That's why we need a numerical simulation. So here we just run this synchronous coupling until they are close together, and then we compare their density. And then you can see that, oh, actually the speed of convergence is really fast. It's exponentially fast. And you can precisely measure this slope in the log linear plot. So this gives you some idea that how fast it should couple. In other words, how fast it should converge to the steady state. And you can move to a lot of higher dimension. So you can have 50 coupled neurons in a coupled physical oscillator. Okay. And then you can say that, oh, I have 100 variables. It's basically not possible to study the spatially discretized or maybe spatial discretized operator. You have to use this probability data-driven tools. And then turns out that the speed of convergence is still pretty fast. So I skip some details. So just to talk about the big picture. Okay, so then we still use this reflection coupling. So meaning that we look for the mirror symmetry of the noise from between two processes. And then we wait until they are close enough, and then we compare their probability density function, and then couple the common part. Okay. And here is the result. So biologically, you can see that when you have higher and higher coupling strength, which is this W and this du. So that's the nearest neighbor, that's the mean field. Okay. So we are changing this nearest neighbor coupling strength, and you can see that higher du means they are more coherent. So that's the heat map about their memory potential. This neuron ID, this time, and the color means that the memory potential. You can see that strongly coupled means that it's more coherent. That's very natural. And then you may want to know, so how fast does it converge to the steady state? Well, turns out that you can get it very accurately, that you can measure the slope in the log linear plot. So they tell you that how fast the speed of convergence to the steady state is, even if you have dimension 100. And yes, the answer is that the more coherent you are. I mean, the more synchronous neurons are, then the slower the speed of convergence to the steady state actually is. Okay. And I mean, you have this for a reason, because think about it, if you are very synchronized, and one trajectory starting from here, the other trajectory start from there, then you have some phase difference. You have some phase difference that it takes the noise longer time to close the gap and to let the trajectory at one phase to meet with the trajectory with the other phase. Okay. So then there are some new extensions that I didn't mention. Is that actually this method turns out that it can also be used to work on the speed of convergence of continuous time function on lattices, or more precisely the chemical reaction. So if you have some biochemical reaction, meaning that you have some Markov jump process on a high-dimensional lattice, and then how fast do you have the convergence? So it turns out that yeah, this method is after lots of twists, yeah, it still work on these lattices. You may wonder how can you couple on the lattices? I mean, in higher dimension, how can you do the reflection? Well, we don't do reflection directly, but we can shadow one Markov jump process with one stochastic differential equation approximation, and then we use the mirror symmetry on the stochastic differential equation approximation. So then there are lots of very technical algorithm details, but yeah, we are able to do this. We are able to couple the continuous time Markov chain as well. Okay. Then the next topic is about the eigenvalue and eigenfunction. So if you study things like neural oscillator, coupled neural oscillator, then that probably is more relevant to you. So the thing is that yeah, let's first talk about mathematics. Okay, so if we have the question we are interested in is that if we have some either some stochastic differential equation or maybe some Markov process, and we have the generator. Then the steady state is actually the eigenfunction corresponding to the zero eigenvalue. And then the question is that how about the other eigenvalues and the other eigenfunctions? So the very first attempt was that let's consider a slightly changed version of steady state, which is the quasi-steady state. So this is essentially one eigenfunction. This is still the eigenfunction, but the good thing is that it's easier to do the Monte Carlo simulation and simulate this eigenfunction directly. So which means, yeah, you can estimate. So this is called the quasi-stationary distribution, meaning that you have a Markov process, but then there is a hole in the phase space such that if you enter this absorbing set, then it's gone. And then conditioning on that you haven't exit yet, then the conditional distribution is called the quasi-stationary distribution. Okay, so the quasi-stationary distribution is the eigenfunction. So this lambda is the killing rate. So the advantage is that you can estimate the killing rate and also estimate this Monte Carlo approximation of QSD directly, because you can simulate this QSD. There are some algorithm of simulating this. Okay, so that's why it's actually not that different from the steady state for Planck. And after that we move to the actual Fokker-Planck eigenfunction. So that's quite important because it's different from QSD. When you do have a Fokker-Planck and then you have the eigenfunction actually the eigenfunction actually makes lots of sense in different areas. For example, you can study the Q function of the oscillator. Or for example, if you study the computational chemistry, then you may know that there is actually a one-to-one correspondence between Schrödinger equation and the Fokker-Planck equation. So which means whatever eigenfunction you calculate for Fokker-Planck, you can immediately find the corresponding eigenfunction for the Schrödinger equation. And we all know that is the eigenfunction of Schrödinger equation called the ground state. That's extremely important in computational chemistry. Okay, anyway, so the setting is the following. We have a Fokker-Planck operator, and that's L, and then we have the generator of the stochastic process. We call it L star. So we have the forward eigenfunction, and we have the backward eigenfunction. We call forward Q, and backward we call it P. And the assumption is that we only have discrete spectrum. So there's no crazy continuous spectrum, and all the eigenvalues behaves good, such that you have this orthogonal decomposition, such that P and Q are orthogonal. Okay. And then the main difficulty for you to compute this, the main difficulty for you to compute eigenfunction is that you do want some information about eigenfunction. Why? Because if you just use the pins, then you can find that the biggest problem is that you will quickly converge to zero, because zero is always an eigenfunction. Zero is always an eigenfunction. So you don't want to convert to the trivial solutions, which means you have to teach the neural network some information about the eigenfunction. It does not have to be a lot of information, but you need something there. And the key observation is that say if T minus S is large, then look at this decomposition, then you can see that all the other terms become small, and the leading term becomes the first eigenvalue and the first eigenfunction. And you can, of course, you can use other approaches to estimate this lambda 1. So for example, if you can just use the coupling technique I mentioned like 10 minutes ago. And for example, you can use the EDMD. But I mean, EDMD, you do this with a lot of care, because EDMD is like sometimes it works magically well in terms of recovering the eigenvalue, but sometimes it just doesn't work at all, because EDMD, it highly depends on how you choose the dictionary. If the dictionary is right, then you can get like first 10 eigenvalues very accurately. And also EDMD can get some approximation of eigenfunction, although it's even worse than eigenvalue, and it's even highly higher depends on the dictionary. Okay. So anyway, then the idea is that yeah, we can take a look at the Monte Carlo data of this transition kernel, and then we take some linear regression, and then you take this because you have data for different t, you have data for different t, so which means you can recover this p and q. You can recover this p and q because what you have is not just one point. You have a time series, and then you do a linear regression of this time series. Okay, so this gives you a approximation of p and q. Okay, so when you have the approximation at some points, then you can say that you are returning to the thing that we know, that I have a PDE and I have some data at some points, and then we can just either do finite element or maybe we can just do the neural network solver, which is actually much more preferred, because you don't need that big amount of data. You only need like a few thousand of collocation points, and then you estimate the eigenfunction at these points, and then you have it. And also there is something about the error estimate. So how accurate is this solution? How accurate is this neural? So how accurate is the numerically calculated eigenfunction? Well, turns out that here the main source of error coming from higher modes. Why? Because when you train a neural network, it turns out that the neural network, it has a very good tolerance to spatially uncorrelated errors. Yes. But on the other hand, if there are some systematic bias in the data that you tell the neural network, then the neural network is very difficult for the neural network to find the right solution. So if you want to get a picture A, and then you tell neural network that you want to learn from picture B, and then you tell neural network that you want to have the operator residual to be as small as possible, then the neural network will suddenly get confused, because on one hand, if the output is A, then you have small operator residual, but on the other hand, you have a Monte Carlo data that is dramatically different, so then it cannot cover. It's basically like if you have letter A with some noise, then the neural network can recover it. But if you tell neural network to learn from letter B, then it can never recover. Okay. So which means the main source of error actually coming from higher modes, because the biggest pollution is coming from the higher modes, means that you have some even smaller lambda, and then you have P and you have Q. So that's the biggest pollution. Okay. So which means you really want to know as many eigenvalues as possible. You don't have to know the eigenfunction, but you want to have as many eigenvalues as possible. And then the next eigenvalue, I call it mu height. Okay. So I want the eigenvalues to be, far apart enough. At least the real parts, I want the real parts to be far apart enough. Okay, and then let's say that I start my regression at some TIS. So this TIS is like if the TIS is longer, then there is some advantage. Okay, TIS is longer, then there are some advantage. But you also, on the other hand, you don't want TIS to be too long. Then you can have some error bound of this regression. So remember that all of those mu, they are negative numbers. Okay. So on one side, you can see that it favors big TIS, because the longer you wait, then the smaller the pollution from higher mode is. So you have small first term. But on the other hand, the longer you wait, then the smaller the difference between your transition kernel and the steady state is, means that you have lots of intrinsic noise, so which means you also have the second part. Of course, you can make up the second part by having more samples. But you also see that, yeah, the samples you need becomes exponentially large. So which means you have to strike a particular balance such that you can, with the reasonable amount of sample, you're not making the randomness to be too high to cover everything. But on the other hand, you want to make sure that the pollution from higher mode to be small enough. Okay. And yeah, that's some result. So that's like still this ring model means that the steady state is a unit circle. And then you are rotating in the plane, and then you eventually converge to this unit circle. And then interestingly, you have the forward eigenvalues. So this and the forward, sorry, you have the eigenvalues and the forward eigenfunctions. So interestingly, that the forward eigenfunctions, they are almost as much concentrating as the steady state. So I don't know the reason, I don't have a proof, but yeah, we do see that the forward eigenfunction has a very nice concentration at the limit circle. But the backward eigenfunction is entirely different. So it's something like this. And we can also do this for the Lorentz. Yeah, so we did this for the Lorentz oscillator with some noise. So remember that the Lorentz oscillator is a butterfly, and then we add some noise. Then the steady state look like some inflated butterfly. Okay. And then we can add, and then we can solve the eigenfunction. And the first eigenfunction look like the following. So you can see that you have something, because I mean the eigenfunctions are complex, because the real part and the imaginary part. And then if you take a look at the time evolution of the first mode, which is exactly why we want to study the eigenfunction. So let's say that let's assume that the first non-trivial eigenvalue lambda 1 and the second non-trivial eigenvalue lambda 2, assuming that they are not crazily close together, then which means after some time, because you have the exponential, so the e to the power of lambda 2t becomes dominantly small. So which means the entire transition kernel is basically approximated by p0, the steady state, plus this exponential times p1 q1. So which means yeah, the leading term of this transition kernel is actually given by your first eigenfunction. So it's actually given by your first eigenpair. So it has a name. So this Q is called the Q function. So this Q function basically tell you that in the long run, how should you rotate? How should you rotate along this oscillator? You don't have to know anything about whether you have limit circle, you have the invariant manifold, you have quasi-periodic orbits. You don't need to know any of those. You only need the Q function. And when you know this, then it will tell you that the leading term, how does the leading term rotate? So that's why yeah, we can apply this to the coupled oscillator, and then we can really understand that intrinsically how is a coupled oscillator working. So that's why you can say that this is Lorentz. So you can actually, if you evolve with the Q function and the first eigenvalue, then you can see that it actually evolves along these two wings of a butterfly like this. So that's some non-trivial extensions that starting from the Fokker-Planck solver, turns out that we are able to also get the eigenvalues and eigenfunctions. Okay, then the last thing is about this singular Fokker-Planck equation. So this is more related to things like real event sampling, things like metastability. And you're also going to see this in some chemical reaction models. So the idea that let's say that if I have some ODE, some deterministic dynamics, and we add a very, very small noise, then what happens here? So when the noise is small, then we know that the solution to the Fokker-Planck should very much concentrated at the vicinity of the attractor. It will concentrate in a way that it's very difficult to represent the solution by either classical mesh-based method or neural network. So because there are some intrinsic difficulties, and say if your mesh is like this big, and your solution concentrated in a very small neighborhood, then then you cannot even represent it by the mesh without very significant error. And then when you take the derivative, then you can see that the derivative is just uncontrollable. The error in the derivative just uncontrollable. And the same thing for the neural network is that basically the bigger the higher derivative is for function, then the harder it is for you to represent it to approximate it by a neural network. So that's why we want to take some decomposition of this singular perturbation problem, and then we convert it to two regular PDEs. So the approach we take is called the WKB expansion. So what is WKB expansion? So WKB expansion says that we have strong concentration. We have strong concentration, so we want to say that this steady state should be approximately some prefactor function z times exponential of minus v over epsilon squared. So this v is called the Freidlin-Wentzell quasi-potential function. Why? Because this is actually coming from the large deviation theory. So it's some large deviation rate function, and there is a variational principle to represent it. Okay. And as I said, most existing numerical methods have lots of difficulties if this epsilon is extremely small. But you are able to solve z and v separately. And then you can convert the singular perturbation problem to two regular perturbation problems. So here are some background that that's coming from the large deviation theory that you have this v, and v solves some variational problem. And therefore, this v actually also solve a Hamilton-Jacobi equation. So what is the Hamilton-Jacobi equation? Well, here this F is your drift, is your vector field, and P is the gradient of v, and this A that's coming from the coefficient of noise. Okay, it's basically sigma transpose. Okay, then the question is that how can we get v and z? So yeah, we know that we satisfy a Hamilton-Jacobi equation, and then if you do a lot more calculation, then you will see that the leading term of z, okay, the leading term of z also satisfy a transport equation. Okay. But the question is that you have equation, then if you train the neural network, then you will most likely get the zero solution, because because in both cases zero is a solution. So which means you still need some data to tell the neural network that where you are. So the question is that how can we get the data for this quasi-potential? Well, turns out that you cannot get the approximation by just using one noise. You have to run Monte Carlo simulation for a few different magnitudes of noise. Usually we do this for 9 or 10. So we run Monte Carlo simulation with different magnitudes of noise. And then you take the logarithm of this WKB approximation, and then you find that you are able to do it because you know that epsilon is changing. The magnitude of noise is changing. Then you take a Taylor expansion of log, and then you do a linear regression. Then you get the training data. You can get the training data of v, and you can get the training data of z in the same manner. Then you can adopt the same idea of training Fokker-Planck equation by a neural network, because you want to minimize the difference from Monte Carlo data and the difference and the residual of the operator. So this H coming from this HJE. Okay. But of course, here there is a big assumption. Big assumption is that do we have this WKB expansion? Well, actually, this is a very difficult theoretical problem. That what kind of ODE, what kind of random perturbation of ODE has this WKB expansion? So the answer is that we know for sure that if there is a stable equilibrium, yeah, we have it. And we also know for sure that if there is a limit cycle, we have it. And we recently there are some big new results say that if this is a invariant manifold, then under some condition, if the invariant manifold is uniformly stable enough, then you also have this WKB expansion. But no, we do not have the general case. But there are some way to verify this numerically. So in other words, so we can at least statistically validate whether we have the WKB expansion or not. So in other words, we want to take a look at is the linear regression trustable? Because if the linear regression here is a very good fitting, then yeah, we can say that we have a good WKB expansion. So the idea is that we want to check the quality of linear fitting, but how can we check? So the answer is that yeah, we want to first take a look at what does the Monte Carlo tell you. Yeah, the answer is that the Monte Carlo simulation give you some binomial distribution, and that's undergraduate probability. The binomial distribution can be approximated by normal distribution. And you take a Taylor expansion, then you can see that so the theoretical error is approximately a normal random variable. And then you can rescale each normal random variable to make sure that the error at different qualification points are identical. So after this rescaling, you can calculate this rescaled residual. And if everything is right, if you have this WKB expansion, meaning that you have this expansion without having any extra terms, then you should have this residual, and this residual should be a chi-square distribution. This residual should be a chi-square distribution with a given degree of freedom. Okay. So which means how can you check whether you have the WKB expansion? Well, the answer is that because you have thousands of collocation points, you just calculate the residual of your linear regression, and then you rescale it, and then you want to take a look at whether you are going to get the empirical distribution of the chi-square distribution or not. So it turns out that in the theoretical case where we do have WKB, then it fits the chi-square distribution very, very well. So that can give you the confidence that whether you have the WKB expansion. And I mean, if you want to, in addition to the quasi-potential, if you want to understand this prefactor Z, then you can do the same thing. You can do the same thing because Z actually satisfies a non-singular transport equation, so you can do the same neural network solver. Okay. And here actually there are a little bit more technical difficulty. If you really train it, if you really train the neural network, you will see that if you do this for the first time, then most likely you will still get a trivial solution, even with the Monte Carlo data. Why? Because first, the Monte Carlo simulation, you only get it in the small neighborhood of the attractor. And secondly, you need a lot more information because and also the Hamiltonian system itself is nonlinear. That's give you additional difficulty. So you need a little bit more information. So basically, you need to tell the neural network that you have 0 value on the attractor, and then you want to set up some artificial value when you're far away because you only have control when you are close to the attractor. But even that's not enough. So a very important part is this data augmentation. How can you augment the data? So the idea is that it's a Hamilton-Jacobi equation. So which means although you don't know V globally, but you do know that you can integrate on each characteristic line of this HJE, and then you know the value of V on this characteristics. So which means you should extend the training set by integrating this V on the characteristics of this HJE. So this will also tell you that what is the value of V on different curves. So again, you don't have the global solution, but you know the information on different curves, and that dramatically help your training. Okay. So let's take a look at that's the Vanderpool and the coupled Vanderpool. So, but for the coupled Vanderpool, actually I take a zero coupling. Why? Because with zero coupling, you are actually making things more difficult from a numerical aspect because you have a invariant manifold, and also it's easier to check. It's easier to check because you know what is the steady state. So for the Vanderpool, I mean, if you run the Monte Carlo simulation, then your training set is like this. So you can see that it's very concentrated. It's not useful. But you can also integrate on the characteristics. When you integrate on the characteristics, then you can see that the training set is expanding, and then you can get the quasi-potential in bigger areas. And then when you get this one, then you can keep expanding. You can just keep expanding and expand to bigger and bigger areas. And this is about the prefactor Z. So usually the quality of Z is lower. So you only have high quality Z right on the right on this limit circle. If you are too far away from the limit circle, the quality of Z is a little bit lower. Okay. And then you have the Fokker-Planck solution coming from the WKB. And in 4D, so meaning that you have two coupled one pool. You can do the same thing. So that's basically showing you how we construct the training set. But this is a projected version. Okay. You can see that that's from the Monte Carlo, and then you also have this from the integrating on the characteristics of the Hamilton-Jacobi. And then you can evaluate the quasi-potential on each slice, because again, the screen is 2D, so you can only plot 2D things. So I evaluated this quasi-potential on different slices, and then you can see that this is basically the same as what we see in the one pool. But here I think the y-axis is flipped, and also we have this Z, and then we can recover this Fokker-Planck solution. Okay. Okay, so I think the time is up, and that's all of my talk and some key reference. So that's about Fokker-Planck solver, about the coupling, about eigenfunction, and about the WKB expansion. So I want to thank all of those collaborators that are involved into this project. Okay, so thank you very much. Mhm.
Going to look at the simulation.
Okay. Oh, which one? Oh, the third one. Oh, yeah, with Max. Yes.
That's the simulation of stochastic.
Well, this is a computational paper. This is a computational paper, meaning that we are not talking about the behavior yet. We just introduce the algorithm. But yeah, I mean, later, yeah, we are working on that. We are working on that. If you do have a coupled neural oscillator, then if it's synchronized, what happens? If it's not synchronized, then what happens? So we do have this project, and we do have this project, and we are working on that. So. But I mean, there are some things that I didn't say that, yeah, so with the current method, there are still some limitation on how high the dimension you can go. So for example, we can do like dimension 4 means 2 neurons are coupled, or dimension 6 with 3 neurons coupled. That's something you can do. But if you give me like 50 neurons, then there are still some intrinsic difficulty coming from the sampling. So actually, there are also some ongoing work that about this high dimensional sample, meaning that if the dimension is if you have a truly high dimensional thing, for example, you have a coupled oscillator and 20 neurons coupled, give you dimension like 40, then how can you use this algorithm? How can you use this neural network solver? So it turns out that the neural network has a strong ability of representing solutions in high dimension, but the bottleneck is actually sampling. So how can you sample in such a high dimension? So there are some tricks here.
The method is not limited by the strength.
No, it's not. It's not.
Great talk. I'm a quantum chemist.
Oh, okay.
I'm more familiar. At one point, you mentioned the one-to-one correspondence.
Yeah, exactly. Yeah.
And Fokker-Planck equation.
Yeah.
And it's by one-to-one correspondence, I mean we can do both forward mapping and back.
Yes, exactly. Yeah, exactly.
How do we have harmonic potential? How do you back? well, Schrodinger equation had a back map to a Fokker-Planck equation.
The answer is that you have to learn this map numerically first. I mean, if you know it analytically, then you can create it analytically. So it's actually a Poisson equation. It's actually a Poisson equation that is very easy to solve because it's like just something like ax equal to b. So if you know this analytically, then you can solve it. Otherwise, you can train a neural network. It converges very fast. So when you have this one-to-one correspondence, okay, then you know that whatever happens for Fokker-Planck, it happens to the Schrodinger. So you can, so for example, the Fokker-Planck equation has the eigenvalue ABC and the eigenfunctions D, E, F, and then you can map everything back to the Schrodinger.
But the Fokker-Planck equation with the noise,
Uh-huh.
what do we mean in the context of Schrodinger equation? Everything there.
Means this Laplacian term. Means this Laplacian term. So in the Schrodinger equation, you have Laplace, right? Yeah. So the square root of Laplace is corresponding to the noise in the Fokker-Planck because Fokker-Planck is elliptic. There is no noise. Fokker-Planck, it's like it describes the term evolution of probability density, but itself it has no noise. So this term, the elliptic term corresponding to the delta in the Schrodinger. So, but I mean, there are some reasons that we didn't really do it because, you know, I believe in quantum mechanics, you are more interested in the symmetric eigenfunction, isn't it right?
Yeah.
Yeah. Yeah, so that's the difficulty that when we have this eigenvalue and eigenfunction, we don't know whether it is symmetric or not. So which means yeah, we can only solve the first few eigenvalues and eigenfunctions, but whether they are symmetric, you have to check it after you have the solution.